Okay, so in this section of video, we want to look at solving equations with the Arrhenius equation. So I just want to rewrite the Arrhenius equation from our last set of videos. So we have the natural log of K2 over K1. So remember, that's our rate constant, is equal to E of A, so that would be the activation energy, over R, and R is our universal gas constant, so it always has the same number and unit. So there's the number and the unit for R that you'll need to memorize. And then we have 1 over T1 minus 1 over T2. All right, so here's the first problem we're going to do, and this actually comes from your textbook. This is problem number 73, or 73, sorry. The activation energy for the decomposition of HI to hydrogen and iodine gas is 186 kilojoules per mole. So the first thing I want to point out to you is that activation energy and our universal gas constant need to have the same units. So either you're going to have to convert both so they're both kilojoules, or you're going to have to convert so they're both joules. The rate constant at 555 Kelvin is 3.52 times 10 to the negative 7th liters per mole per second. And we want to know the rate constant at 645 K. Okay, so I'm going to opt to make T2 the higher of the temperature. So that means we're going to be solving for K2. And I chose to convert my activation energy to joules. So that would be 1.86 times 10 to the 5th. Okay, so I'm going to solve this part of my equation first. And remember, we're not going to round to the very end. So when I solve, this is what I get. I get 5.62461415. Okay, so again, you should be pausing the video and using your calculator to make sure you come up with the same values that I have. And we didn't do anything to the other side of our equation. Yet. All right, now here's what we want to do. We want to get rid of this natural log. So that means we're going to have to take the inverse of the natural log. So e to the power. So we get rid of the natural log on this side. And we're going to take e to the power of 5.62461415. Okay. So when you take e to that power, you should get this value. Okay, then we want K2 by itself. So to get K2 by itself, we're going to multiply both sides of our equation by 3.52 times 10 to the negative 7th. And we should get an answer of 9.8 times 10 to the negative 5th. And the order of reactions would be the same. So the rate constant unit should be the same as it was in K1. We get liters per mole times seconds. That's our correct answer. All right, and then we have one more problem we're going to look at here. We're going to do number 75 from your textbook. And so in number 75, we are given that the activation energy, we're given one of the temperatures, and then we're given the factor by which the rate constants are going to change. So again, we're going to use the Arrhenius equation. So here's what we're going to do. Again, we want to make T2 our higher temperature. So we have a ratio of K2 over K1. And in the question, it tells me that the rate constant increases by a factor of 7. So we're going to make K2 7 and K1 1. Okay. Now again, my activation energy has units of kilojoules, so I needed to convert that to joules. And we know the universal gas constant. We would need our temperature to be in Kelvin. So just a reminder, you're just going to add 273.15. And so we get 295 Kelvin. And we're going to be looking for T2. Okay, so this is what I did first. I took the natural log of 7. And then I divided out my activation energy divided by my universal gas constant. All right, then I wanted to leave this temperature part of my equation by itself. So we're going to divide both sides by 6,495.068559. So this is a decimal. Okay, so again, you should be pausing your video and doing your own calculations to make sure you come up with the same answers I have. And we don't round into the very end of our calculations. All right, so then we want T2 to start to be by itself. So we're going to subtract this 1 over 295 from both sides. And so now I have this. So we're going to take the negative inverse of both sides. And so T2 is going to be equal to 324 Kelvin.